Hello everyone. Today I'll be presenting our group project on AES 128 hardware software co-design implemented on Cyclone 5 SoC FPGA for the course design and analysis of reconfigurable systems. So here's the content slide. This presentation covers the motivation, system architecture, AES algorithm overview, HPS and FPGA design, communication, verification, and performance results. So in this, let's discuss about the motivation objective. AES is a widely used cryptographic standard, but software-only implementations can be slow for compute-intensive applications. The goal of this project is to build a complete hardware-software system where AES 128 encryption is accelerated using FPGA hardware, while the HPS handles the key generation, user input, decryption, and verification. Our system consists of hard processor system and FPGA fabric. The HPS communicates with FPGA using memory mapped Avalon interfaces. The FPGA responsible for only for AES encryption, while HPS manages control data transfer and validation. AES 128 is a symmetric block cipher with 128-bit block size and key size. It performs 10 rounds. Each round applies sub-bytes, shift rows, mix columns, and add round key operations, with the final round skipping mix columns. On the HPS side, AES-C core runs on the ARM processor. The software generates a random 128-bit key at runtime and reads plain text input from terminal. The HPS also performs software encryption and decryption, which acts as a golden reference to verifying the FPGA output. The FPGA implements a custom AES 128 encryption accelerator. It accepts 128-bit plain text and key and outputs a 128-bit ciphertext. Only encryption is implemented in hardware to reduce complexity, by decryption is handled by HPS. So here's the FPGA communication. Communication between the HPS and FPGA is done using memory map registers. The HPS writes plain text and key data to the AES accelerator and triggers encryption. After encryption completes, the FPGA writes the ciphertext back, which the HPS reads for verification. This is the verification and results slide. To verify correctness, the ciphertext generated by the FPGA is decrypted in software on the HPS using the same key, AES key. As shown in the terminal output, the decrypted plain text matches the original input, confirming the correct end-to-end operation. You can check it here in the form of hex and ASCII. So here's the given input. So here's the FPGA resource utilization. It shows the quarter's resource utilization report. The design uses moderate number of ALMs and registers with no DSP blocks. Overall resource usage is reasonable for an AES 128 accelerator. Timing analysis is performed using Quartus timing analysis. The critical path is approximately 25 nanoseconds, which corresponds to a system frequency of around 39 megahertz, where when we report Fmax summary, we get the maximum of 1184.83 megahertz. So in conclusion, we successfully implemented AES 128 hardware software co-design system on Cyclone 5 SoC. The FPGA accelerates encryption while the HPS manages control and verifies correctness. This project provided valuable experience in hardware software co-design and FPGA based acceleration. Thank you, and now we'll give the demo of the project.